talk about Smith charts. I got a bunch here if you need, or some more if you need. Anybody need them? Just get them and pass them out. Now these, I sent you an enlarged one that's really good, high res one. If you print that off and use it, you'll be thankful. It'll really help. I'll leave them right here. If you need it, just come up and get it. But before I do, I want to go through the homework. And any questions you have about the homework. Now, so far, we did the complete circuit last time, didn't we, class? Are you all working on this? How many looked at the homework I put up? All right, hopefully you got a chance to do it. This is a little more complicated. Are there any questions about any of the problems or anything like that? Nothing at all? All right, I want to tell you, that is not a trivial thing. The complete circuit is a problem. I'd like to do something to see if you got it going. Let me know. What was it?
You just want to do anyway, so the view right here.
All right. Okay, you got it. Thank you, that's awesome. This is my copy. Test it. Can you hear me okay? Is this mic picking me up? Or not? All right. Anyway, what I want to do is this. I'd like to do one quick problem related to complete circuit. That way, I'll feel comfortable that I'll address your question. I'll ask the audience, see how you respond. So I'm just making this one up off the fly. Suppose we have a 10-volt source at 0 degrees. This is going to be volts. And I have a resistance here of 50 ohms. And then I have a transmission line. And let's say the transmission line, if you have your calculators, get them out. L is equal to lambda over, say, 8. Lambda over 8. And it has a characteristic impedance here equal to 50 ohms. And then I have a load here of, say, 20 minus J 50 ohms. And I want to know the voltage developed here, plus and minus the voltage. All right. And I want to know the current, I of L, into the load. And finally, I want to know the power, average power, absorbed by the load. So how would you go about doing that problem? And you can give yourself a frequency, but it doesn't matter. If you have lambda over its length, that's all you need. Now, how do you do this, class? What's the first thing you would do? Anybody? If you've done the problem, you should know. Go ahead.
Find the reflection coefficient?
You can do that, sure. That's going to be needed, so we might as well find the reflection coefficient right here. So, what is the reflection coefficient? You're absolutely right.
It's ZL minus ZO over...
Yeah, you're going to need to know these, and you'll know them if you do a bunch of problems. ZL minus Z0 over ZL plus Z0. If you have your calculators, do this with me. Give me that value. ZL is 20 minus J50. Z0 is 50. So 20 minus J50, right there, minus 50 is going to be minus 30 minus J50 over the sum. Can you all see what I'm doing, right? Can you give that to me? Anybody? Now give me a magnitude and angle. If you got your calculators, get them out. Here's where mistakes will be made in Friday's quiz. Guaranteed. I mean, I'm not a prophet, but pretty much I can say people are going to mess this up. I feel very confident based on everything I've seen before in this class. And this is a large class, too. Can you all see this okay and hear me? Okay. Anybody? Now, this should take you literally under a minute. And you get used to your calculator and used to doing this. I look at that, and I see what? I see minus 30 minus J50 over 70 minus J50. The sum, it should be a magnitude and angle. You should be able to do this. Anybody? Please try it on the calculator. I'll warn you if you don't, come Friday, you may convince yourself you don't need to do this, but it will be a disaster. Matter of fact, you were in my office a bunch of people and I asked her to do this, not this, but something similar to this, and she saw the wrong answers appear. Anybody?
It would be 0.05.
.05?
Yeah, I'm not really sure if this is incorrect.
How about
Someone else.
667
Hold
at
on.
an angle of negative 85.
0.667 at an angle, say it again?
Negative 85.
Oh.
And I messed it up. I said it's 677.
677, 0.677 at an angle of minus, say it again?
Negative 85.
Minus 85 degrees. All right, just see if you get that. All right, it's simple. Doesn't take a second. Should be able to do this almost seamlessly, like V equals IR kind of stuff. All right, I've got that. You need that. You want to go on to the next step? You're right about that.
Find Zn.
Yes. You can look at your notes for now. All right, so I need the Zn right here. This is the one you're going to mess up. Get your calculators out. Please work this with me. I'm trying to do you the biggest favor. All right, so what is Zn? Well, I'll give you this one on the quiz, but you need to know what everything means in this formula. Z0 is the characteristic impedance of the line. This is ZL. It's a complex number plus JZ0 tangent of beta L, don't do anything yet, over Z0 plus JZL tangent of beta L. Now, some of you remember me talking about beta L being critical because that's going to be something that gives you the argument of the tangent function, and it will be in radians. Let me say that again. It is not in degrees, it's in radians. Do y'all hear me? So beta is 2 pi beta L. So beta is 2 pi over lambda. What's the length of the line, class? Can you see it? Look. Lambda over 8. You'll notice the lambdas cancel. That's why you don't need a frequency. So you have 2 pi over 8 or pi over 4. Now, if you want to use degrees, what angle is that in degrees? Anybody? 45, right? You can put pi over 4 radians in your calculator, and if you can put it in a radian mode, just do that. So then, I know I'm going to have the tangent of that here and here, right? So you might as well just get the tangent of that, put it in a memory spot. So what's the tangent of pi over 4? Opposite over adjacent, 1. Isn't it, class? Strange, I chose that number. So this is 1. 1's an easy one to work with, right? 0's even better, but 1 will work. Now, what next? What is Zn? Z0 is just 50. I'm going to leave it as Z0, right? Then it's times ZL plus JZ0, because the tangent is 1, over Z0 plus JZL. What do you get for that? Go ahead. Y'all agree with this? Please use your calculators. See if you get it. What I'm telling you is going to help you. And you had me for a while, and I think some other people in here have had me or seen me. Trust me on this one. This is where mistakes are made at an incredible rate. I would bet 2/3 of the class make mistakes right now trying this. Anybody? Well, Z0, nice thing, it's 50. ZL's got a real complex number, right? Some of you will probably do the right thing and add these two together. You get a single number, right? Then multiply by Z0. But what do you get? Anybody? There are no wrong answers. Just throw some. You got an answer? You don't have a calculator?
It's dead.
Well, make it alive by 5. That's the other thing. My calculator's dead. I'm so sorry. Bury it and buy another because you're going to need it. Anybody? By the way, don't trust me if I just throw down a number. Be suspicious. See if it's right. Now, there's no wrong answers. Anybody got it? How about it? You can give me real and imaginary or magnitude and angle, either one.
11.6 angle 35.5.
11.6 angle of 35.5 degrees. Anybody else?
That's what I got too.
All right, store that in your memory. You got that? How many got that? I heard somebody else say it. You got it? You got it? Anybody back there get that? Nothing? You got a different answer? You got it? You're gonna need to do this fairly quickly. Remember, the quiz is 10 minutes. This is a quiz problem, promise you. I'm not joking. This is a quiz problem. This kind of thing is a quiz problem. So you have to do these things fairly efficiently. Anyway, we're gonna go with this in ohms, all right? Now, what he said is absolutely right, but what do we need next? All right? Now we've got the input impedance here, but what do we really need from that?
The
Well, the equivalent circuit is what? It's plus to minus 10 at an angle of 0 degrees, volts. Forget the 0 degrees. Now it's got a resistance here of 50 ohms, and now it has an input impedance of 11.6 to 35. You can put real and imaginary if you want here. So this is 11.6 at an angle of 35 degrees. And I need this voltage that I'm calling V prime. Don't I, class? You all follow me? That's the voltage I need, right? That's the equivalent of the reflected, forward-going and reverse-going voltage at the point where the actual source is connected to the input of the transmission line. By the way, I have a transmission line. It's just a coax cable I wanted to pass around. Where is that thing? Is it being passed? Did you pass it?
I passed it. I don't know where it went.
Oh, it's back there. Keep passing it around. So everybody, this is a transmission line. If you've never seen a coax, you're in for a treat. All right, so do you all agree with this? Now, what is V prime going to be right here? Just look at it. V prime is going to be simply this impedance, the input impedance, right? 11.6 at an angle of 35 degrees. You could have left this in terms of real imaginary. Over 50 plus 11.6 at an angle of 35 degrees. That's the voltage division times the source voltage at 10. Now you're going to get a voltage there. Give it to me, please. With a little more, I guess, concern from getting it done correctly. You got a calculator or not?
Can't see the.
All right, I just take the input impedance divided by the input impedance plus 50, or plus RS, and multiply it by 10. You all follow me on why I'm doing this? That's voltage division. That would be the input voltage at the input of the transmission line. Does everybody follow me? Give me a show of hands if you do. If you don't have calculators, I'm sorry, I wish you did. You're going to need to know how to do this efficiently. Usually I have people that don't know why they get the wrong answer, and they're clueless. But somebody else in the class when we're doing this gets the right answer. And the only thing I do is point to the person that doesn't know how to do it and point to the person that knows how to do it and tell them to get together and figure it out in class. That's the only way. I mean, a lot of the calculators, I think you use TI 89s, TI 84, 85, Inspire. One or two people have HPs, but usually there's at least somebody else in the class with the same calculator can help. Okay, what'd you get?
1.88, angle negative 9.6, e to the negative 14, times 10 to the negative 14.
Oh. Hold on.
My calculator.
Minus 14 is 0, right? 10 to the minus 14 is 0. Look, I've got 11 ohms. Call it 11 ohms. Well, times 11 over 50 times 10. That ain't 0, is it, class? All right, first mistake. That's all right. Pretty sure it ain't 0. Y'all with me? Yeah, what'd you get?
1.94, an angle of 29.05.
1.94, angle of 29 point what?
0.05.
05 degrees, right? You agree with that? Anybody else get that? Okay, you get.
Like that times 10 to the negative 1. So like one significant digit less.
You got 0.19?
Yeah, 0.194.
Now, you probably forgot to multiply by 10.
That's what I did.
You multiply by 10?
I did not.
Okay. Mystery solved. All right, you need to. You all with me on what I'm doing? I want to make sure. Next step is critical. This is Mistake City coming up. Ready? I've got to go over here and do this part. Anybody know what I'm going to do next? I got V prime. What's my next step?
would you get the I load, the current, or
V prime doesn't give me the voltage at the load, does it? V prime is that. What do we need to do, guys? Complete circuit. Anybody? For 50 points. It's like Jeopardy. What do we do next for 50? Well, we set V prime equal to V naught plus. That's the key, V naught plus. That's what we're after. That will give me the rest of the problem. And that's always times e to the minus j beta z normally, right? But where are we at the load here, we always put in z equals 0, right? So if that has that length, this is z equals minus lambda over 8. You all follow me on the reasoning. Remember that. The length is lambda over 8. We say z equals 0 there. That's positive z. This has to be z equals minus lambda over 8. You all follow the reason on this. So when I do this, normally it's e to the plus j, or e to the minus j beta z, but z is minus lambda over 8. So this becomes e to the j beta L. I'm going to put this down this way for a reason. Plus the reflection coefficient of the load times e to the minus j beta L. And I note that beta L is really the 2 pi over lambda times the length, which is lambda over 8, so it's pi over 4. Do you all agree with that? Now, if you want to work in degrees, we can replace beta L by pi over 4, but that would be e to the j 45 degrees. Do y'all follow me? If you want to leave it in radians, you can. What I'm going to do now, and here's where you get into trouble. I'm going to take this. We're after V0 plus. This is equal to V prime. So that means V0, take your calculators and do this with me, is equal to V prime. Now V prime is over here, and that has an argument in degrees. Then it's going to be over e to the j. If you want to put in degrees, you can put 45, or you can put pi over 2 radians, or pi over 4 radians, pardon. And then it's going to be plus the reflection coefficient, which, did I erase that? No, there it is. The reflection coefficient at the load, right there, times e to the minus j pi over 4. I'm going to tell you this because they put this in terms of magnitude and angle in degrees. You may want to put this in terms of degrees, of 45 degrees, minus 45. Do you all hear me on this? Now please try this with me. How many have calculators here? Just show me. Please try to do this. This is where the mistakes occur at an unbelievable rate. And tell me what you get for V0 plus, magnitude and angle. Go ahead. It's the only way I can get people to do this seriously. Thursday night they start trying it, they don't know what they're doing. Send all sort of panic emails. I can't be plus. I'm dying. So sad. You get it?
What is the notation next to on plus?
What, this?
Yes.
That's gamma L. That's the reflection coefficient right here. Are you with me, class? Anybody? This will take you a little bit of time. Just remember, doing this saves lives, your life. I don't know, Dave Irwin may use your calculators in class to figure things out. But there are going to be people that don't know what in the world's wrong with what they did, but they get the wrong answer. And somebody with a calculator knows how to do it usually and can straighten them out. Yeah?
I can't see.
Oh,
Sorry.
sorry. Don't forget the pen. Anyway, and remember, no wrong answers. Just tell me what you get. Anybody got it yet? This should take about 2 minutes at most. This is how I structured the quiz. I know about how long each calculation should take. If you know what you're doing, you'll be done with it in no time, probably about 7 minutes. If you don't know what you're doing, you're panicking at the end, you'll probably not have a clue how to do it. You got it? Okay, what did you get?
Wait, let me convert it to polar.
Magnitude and angle. Did you get it or not?
I got it in rectangular form.
Put it in polar if you can. You should just have a couple of buttons to press. You should go like rect to pole and just magnitude and angle comes in. On most calculators that I know. Did you guys get it?
It's not.
How about you? Go ahead. You didn't get it? What didn't you get?
I got an error.
Ah, yes. That's what I was waiting for. I got an error.
Yeah.
You're going to get an error. Believe me, you're going to get it. All right, I'm going to show you something right now. All right, if you all agree that I've got deep time over there, right? That's just magnitude and angle, right? So I'm going to put that up here. So what is that again? That's 1.948. We'll call it 29 degrees. And it's at an angle of 29 degrees. Now, this is e to the j45, right? E to the j45 is the cosine of 45 plus j sine of 45 if we use Euler's. Do you agree with that? What is the cosine of 45 degrees? Anyone? What? 1 over square root of, isn't it? 1 over square root of 2? What is the sine of 45? Same thing. So I can put this as simply 0, this is the first term, 0.707 plus j 0.707. That's 1 over square root of 2. The reflection coefficient here was 0.667 at 85 degrees. So I have to say plus 0.667. And this has an angle. I can put e to the minus j 85 degrees. If you want to leave it in degrees, make sure your calculator is operating in degrees. It's that. And then it's times this. Well, this again is 0.707 plus j 0.707. Now the only thing I've done here is I've expanded, and it's actually minus, pardon, this is minus j 0.707 here. Can you all follow me what I did? Yes, sir.
I have an answer.
Good. What is the answer?
1.27 angle 2.7
2.7 degrees?
radians.
Radians, okay. Can you change that to degrees? Just multiply by 180 and divide by pi. It's about 57 point something. 110 degrees?
73.17 angle 2.7.
Degrees? That's you said radians.
Oh, sorry. Give me a second.
It should be over 100 degrees. Anyway,
I got something, but it wasn't over 100 degrees.
what did you get?
I got 1.55 at an angle of 16.7 degrees.
You got that? I'll put it up here. You got 1.55 and an angle of, say it again?
The angle of 16.7 degrees.
16?
Yeah.
0.7 degrees, so this is 1 V naught. Anybody else? Yep, you got that?
Yeah. I got 5.47 at angle of 159.78.
5.47, angle of, what's it again?
159.78.
159.78 degrees. All right, how many see that there's a lot of variety and there's only one right answer? This is where you have to know how to do your calculus. It's the only thing I'm showing you today. If you don't know what you're doing, you're going to fail miserably. And there's no partial credit for a lot of this stuff. I mean, zip it. Because you got to know how to use your calculators. I give you partial credit on some things, theoretical proofs and the way, but not this. This is one you got to know. If you're an engineer, you're paid a lot of money to not make mistakes. So you don't spend a couple $1 billion losing things on Mars. So you have to know what you're doing with your calculator. All right, now I'm not sure the right answer to this one, but I can get a pretty good idea. When I take a look at this, what I've done here, I can see that I have, the big trick is this. Now, if I take this right here and multiply, that's almost 90 degrees. I'm going to show you an approximate way to do this. I take a look at this and I'm going to say this is about 2, this is just an approximation, about 2 at 30 degrees, just leave it as such, and I'm rounding here. This is really, I'll call it 0.7 plus j 0.7. Now I'm doing this just because I'm trying to get an estimate, not the exact value. You with me? Next I take a look at this. E to the minus j 85 degrees is just about minus j. You all hear me on that? It's almost e to the minus j 90. So I'll just make that minus j right here. Just watch this. So I can make this minus j. Now, some things start coming into focus. I can see when I have 0.667 times 0.7 times minus j right there. I'm going to have minus j, and this is about 2/3, so it's about 2/3 of 0.7. And then I have minus j. Well, j times j is minus 1, right? Minus times minus is plus 1, so it's going to be minus, and this is going to be about 2/3 times 0.7. Now, only thing I'm doing is a rough approximation, right? I'm just trying to get things in a ballpark. Take a look at this. For the real values, I have 0.7 minus 2/3 of 0.7, or I have 1/3 of 0.7. Do you agree with this, class? Y'all follow me? That's 0.7. That's minus 2/3 of 0.7. It's about 1/3. I can just get rid of this and take this and divide by 3. Now for the imaginary part, I have 0.7 minus 2/3 of 0.7. Do you all see this? So what is that? Well, that is about what? It's about j 0.7 over 3, right? All right, you can see really what's going to happen now, and this is just an approximation. There's nothing very close to 0 here. This is really, downstairs everything's divided by 3. We can multiply both sides by 3, and I get 3 at an angle of 30 degrees, divided by, and now it's 0.7 plus j 0.7. That's really about 1 at an angle of 45 degrees. That's what it is. So I can say this is divided by 1 e to the, or 1 at an angle of 45 degrees. And if you look at this, this should be about 3 at an angle of minus 15 degrees. Anybody get anything close to that? Go ahead.
Should be 6 in the numerator because the.
Oh yeah, sorry, 6. My bad. You're right. Absolutely right. This should be 6. This should be 6. At an angle of minus 15 degrees. Close to that. Did anybody get something close? Anybody at all? You did? What'd you get?
I had 5.98 to -6 on 11 degrees.
All right. It's close, and again, I approximated, so I can't say what I did is exactly right, but you all follow me. That's how you get something close. You might be right about that. Now, did anybody get something that has a magnitude of about 6? He did. Anybody else? What did you get for your angle?
-6.9.
And you got minus 6.9?
6.1.
6.1, 6.9? All right, there might be an approximate. Anybody else get close to that? I'll bet you something. I bet you that's right. And I'm going to tell you, you need to know how to do these things on your calculators without making stupid errors. Mainly it's degrees to radians. I'll give you the answer to that one if somebody emails me when I get out of here, all right? But I wanted to make sure everybody saw that. Now we've got V0 plus, right? Let's assume we got it. We're going to use, how about we use your value? What did you get here? We'll assume V0 plus is, go ahead.
6,
5.9 at an angle of,
-6.1.
we're going to assume that's right. Y'all with me? I'm just making an assumption. Next, after V0 plus And I'm gonna have to erase some of this for me to do, well, maybe I'll do it over here. After that, right? Now, what do I need? Anybody. I've got V0 plus, right? So now I know for this general equation for V of Z, I know V0 plus, which I've got, times e to the minus j beta z plus the reflection coefficient times e to the plus j beta z. I know that's an equation for voltage anywhere on the line. Is it not, class? Y'all with me? I have V0 plus, I have the reflection coefficient. What is the value of Z here at the load?
0.
It's 0, right? That's where you always put the load at 0. If it's 0, what happens to this equation? That is the voltage at the load, right? Is equal to V of Z equals 0 on the transmission line. And that's simply V0 plus. Well, what is e to the j0? Anyway.
1.
It's 1 always. So I have 1 plus the reflection coefficient times 1. That's the voltage at the load. So what is the voltage at the load? You've got V0 plus. It's an assumed value right here, 5.9 at minus 6.1 degrees. So what is the voltage at the load now? Now remember, gamma L is complex, real and imaginary. Just tell me the magnitude and angle of that. Please get your calculators out and try this. There's horrendous mistakes made here. This is V0 plus, you can put it in radians if you want. 1 plus gamma L, that's almost minus J right there, almost. Anybody? By the way, what I just showed you in this problem, this is a typical quiz problem. Typical quiz problem. Keep that in mind. Now, some of these people have already seen what I give. When I say that, I mean that. Anybody? What'd you get?
My calculator is being buried right now. It's
Another
not like.
calculator buried.
Yeah, sorry.
I have a service after. Yes, what did you give me?
7.4 at an angle of negative 39 degrees.
7.4 at an angle of 39 degrees. Anybody else? You got that? Anybody else? Back there? Far back. Did you guys get it back there? You got it? Looking like a lot of people got it. Down here, do you guys get it? Still working. A lot of times you don't know how to do the polar stuff. You don't know how to enter a number in polar coordinates. Sometimes you don't know how to change from radians to degrees or degrees to radians. There's all these little things that you have not been asked to do as a common thing, so you're getting used to it. Y'all with me? All right. Now, I'm going to assume this is right in volts. I'm going to assume that. That means I got the voltage at the load. Now, somebody else, tell me, how do I get the current at the load if I have the voltage at the load? Anyway. Yeah, basically what do I do? Take that voltage and divide it by the load impedance. Isn't that right, class? Divide it by ZL. Do you all hear me? That's it. If we wanted the current, we might as well get it right here. If I wanted this value of IL, I would take that voltage, 7.4, at 39 degrees, and divide it by 20 minus J50. Now, I usually ask for numbers in polar coordinates, not always. Polar is magnitude and angle. Rectangular is real and imaginary part. Either one has the same information, but you need to know how to do both. So what is that going to be? Yes?
It's supposed to be negative 39 degrees.
Oh. So this is minus 30, my bad. Minus 39 degrees. And this is minus 39 degrees. So what do you get for that? It's good. gonna be a little greater than a 1, and the angle I'm not absolutely sure of. I think it's gonna be positive angle though. Anybody? Give it a shot, guys.
You want it in rectangular or polar?
Just polar.
0.137 at an angle of 29.4.
Anybody confirm that? You got that in the back? Probably true. All right, we got voltage, we got current. How do we get power? Average power. You remember what I told you? The power dissipated at the load would be 1/2, right? Normally, they put down the real part of the voltage at the load times I conjugate of the load. But I told you a simpler way last time. You remember? Power is only dissipated by the resistance value. So I can say the power is simply 1/2 the magnitude of the current, there's no angle here, times the resistance. Or it's 1/2 magnitude of the current, you have a 0.137 squared times the resistance. The real part is 20. Can somebody tell me what that is? That's not a hard calculation. You're squaring one number and multiplying that number by 10. You get it? What'd you get?
I got 18.77. Oh, never mind.
That's 0.137, so that's
0.187.
0.18, say again? 77 watts. Anybody confirm that? You got it? All right, class, this is a characteristic problem. Typical thing you're going to see in the quiz on Friday. I'm going to start with Smith charts now. I don't have a whole lot of time. But I want to warn you about one thing. Please, if you don't know how to do these efficiently and quickly on your calculators, do them today. Talk to your friends tomorrow if you mess up. Because if you don't know, you'll get killed on Friday. I mean, you'll get a 0. I'm trying to help you, all right? And it's really, really important that you follow through on this. Okay, enough? Yes?
Is the 0.137 using the
You don't need an angle. Here's the reason. That's magnitude of IL squared. Remember, when you had power dissipated in a circuit, in any kind of circuit that's an AC circuit, inductors and capacitors dissipate 0 average power. Only resistors dissipate power. And the power is always magnitude of I squared. And it's divided by 2 because the peak, we're using the peak value of current. If it was RMS value of current, it would just be I squared times R. Yeah.
On the quiz Friday, are there any formulas given?
Well, I'll give you a Z in, that complex formula, but you have to know the rest.
Yeah.
And so I'll give you a Z in,
Okay.
all right? But the only way you get this in you is do a lot of problems. By the way, speaking of that, did you guys find the PDF of that thing?
I haven't looked through it yet, I'm sorry.
No?
I found the 6th, 8th, and 9th edition, but
That's
the
fine.
6th doesn't have any problems, and the 8th and the 9th are the same.
There are solutions for that. Send me an email, see if I can get some. All right, now with Smith charts. We're going to start Smith charts, but you need to work these problems with a complete circuit. Completely. And remember, hear me on this. I'm not trying to be mean, but you have to learn how to do this. Almost no partial credit. Just about. You'll get something for your name if it's right. Yeah, take some. Okay. Now we're going to talk about the Smith chart and things that make this problem easy. I'm going to tell you the Smith chart is your savior. It makes this problem easy. Well, easier. Might be a loose term.
Like, I'm trying to understand how to do polar. I can do rectangular. I can do everything in rectangular, I just can't do polar. So if I'm Yeah. I know how to convert it.
So,
If you don't know how to use your calculator to do one thing, I'm going to recommend you Google it. Get on either use Yahoo, Google, something like that, DuckDuckGo, and look it up and figure it out. All that stuff's out there. YouTube has enormous amounts of information about how to use every calculator on the planet. So they'll have some. Next, what I'm going to do is, now we're talking about the Smith chart. So I could go through and do the derivation of it, or I could try it. I think anyway, the derivation of the Smith chart is not very interesting. It takes some time. It's done in his book. What is of interest is how to use it. So here's how I started. I first put up where the Smith chart is. And you're going to see a big old circle like that. It really is a graph of the reflection coefficient, magnitude, and angle, but that's only the beginning. Next, what I do is put the equator in the Smith chart, a horizontal line dividing the upper and lower part. Then, put a cross right there, right in the center. All right. This is a point that will become very important in a second. Now, what you're going to see are circles. The circle of importance first to see is this. And you're going to see something on that circle that says R equal 1, or something like that. That is a circle that we're going to use for a lot of things. You're also going to see trajectories like this that are perpendicular. This is J plus, and this is going to be minus J. They're at the north and south poles, and I'll explain this in a second. Now, what you're going to see are circles that do this as such, and they get smaller and smaller. This will be like R equal 2, R equal 3, and so forth. Then you're going to see trajectories like this, where this will be, you'll see a value of 1.2 J, and it's assumed J. Now, here's what this means to you, and I want you to listen to me, because once I talk through it, everything becomes clear. What you're doing with the Smith chart is, it deals with the typical problems we have with transmission lines, and it makes them easy. So with the Smith chart, if you have a load impedance here, and you have a characteristic impedance, Z0, and we want to know, I don't know, maybe we want to know Zn, but we're going to go through everything we can know about it, and Zn would be for anything that we get in length L. Now, can everybody follow me? I just showed you this is what we've been talking about before, right? So here's how you use this Smith chart. The first thing you do is find something called the normalized load impedance. That's the capital ZL over Z0. Now, that will have a real and an imaginary value. You all hear me on this? I'm going to call the real value R and the imaginary value JX. They're both small. So this is normalized. The next thing you do is come over here and realize all these circles that are basically centered around the equator. Yeah.
What's that symbol that you have for one? The
Here?
no your one then the one right next to it. What's that?
This is ZL. It's called. You can say it's ZL, but it doesn't matter. I just do a script ZL. It's always. I'm sorry about that. All right. Now you come in, and all these circles that are symmetric about the equator are real values that are normalized. So you find the one that has that real value. Let me give some numbers to this so I can talk my way through a little better. Let's see if it's 1/2 plus J 1/2. So I'm assuming that's the value when it's normalized, okay? If I do that, the 1/2 circle for R is about here. You're going to see R equal 1/2 here. This is this circle. Get a different color here. So it's this circle, about. You can take a look. And then J 1/2. Well, this is J1. J 1/2 is going to be about here. Now, they don't have the J usually on these things. It's implied everything in the northern hemisphere is plus J, southern hemisphere minus J for the circles that are perpendicular that intersect. The trajectory is perpendicular to the edge of the circle. Y'all with me, class? When you look at this, you should find the point where it's 1/2 real and imaginary 1/2. This is your first point. This is where ZL is. Can you look at this, please, and find that point on your Smith chart? Don't mess around here. This is critical. That's called the entry point of the Smith chart. I put up a bunch of YouTube videos about this that a woman does, I think, in Colorado State. They're fantastic. Can you see it? How many see it? 1, 2, 3. You see it over there, Jeremiah? No? Can you show, just look behind. Do you see it? Anybody not see that point on a Smith chart? Y'all see it?
It's,
Back there, you guys see it or not?
since it's 1/2
Over here.
and 1/2. So you
No?
go one, you go find this
Anybody
value,
not
value
see that
is-
point?
And then you find your imaginary value, which is, J, whatever. And then, so these curved lines are your J, are your imaginary. And then this straight line's your real.
Everybody okay with that?
Find your real,
Hear me now.
find your J,
All right,
and that's
look.
it.
Next, draw a straight line from the center of the circle through here, like I'm doing. You with me? Now, the length of this line is the magnitude of the reflection coefficient at the lobe. I'm just about I am on top. If you go to the very bottom of your Smith chart, you're going to see straight lines, and something will say REF coefficient. Do you see that? REF coefficient. It's the very bottom. You've got a Smith chart there. Can you see it? Now, if you take this length right here, and you go to the bottom of the Smith chart, give me 1 second on this one, and you take a look, you're going to, it'll say like REF COEF, something like this. What? Does it say RFL?
RFL.
All right. All right. Reflection. All right. RFL. And what you're going to see is something like this. Now, what you end up doing is going and measuring the length of that line on this, and you're going to see the longer the line, the closer reflection coefficient should get to 1. Can you all see that? So you start, I usually started in the center, and the longer the line, the closer reflection coefficient is to 1. Can you all see that? What's the reflection coefficient magnitude for this one? Just tell me. We can get this fairly easy, right? I know I'm about out of time. Anybody?
It looks near 0.2.
0.2?
Yeah.
At what angle? You can calculate this using the equation ZL minus C naught over ZL plus C naught. You get the same answer.
I have a question.
Yeah.
So what are we measuring to get the number at the chart on the bottom? Like the length of the line?
Yes.
from the center to
Take
the
your
outer?
compass. Take your compass and just do this. All right? Or any measuring device you have. And then go down the bottom, you put it there, and you're going to see that that will be the magnitude, not the angle.
It's not 0.2. Never mind.
What's that?
Never mind.
Is that wrong?
Yeah.
He said that he was wrong. Like
He's wrong?
Yeah.
All right. If he's wrong, somebody I hope is right. We're about out of time, but if we wanted it, we could do what? Just if Z naught is 1 and this is 1/2 plus. So you take ZL minus that, so it would be minus 1/2 plus J 1/2 over ZL plus that, or 3/2 plus J 1/2. Go ahead. Anybody get the answer for that? Magnitude? Anybody?
It's probably, it's 0.45 now.
0.45 sounds a little bit closer to the truth. What angle? I'll tell you how you get it. if I make Z naught 1 and ZL 1/2 plus J 1/2, that's the normalized value. Take a look at this. I know the reflection coefficient is going to be the impedance I go into minus the impedance I came from. So it's minus 1/2 plus J 1/2 over the sum. And it would be over 3/2 plus J 1/2, right? This will give you the magnitude and angle right there. And it should be very close to what you're looking at. I'm going to have to pick this up on Friday because I'm out of time. Would anybody get the right answer for that? Can anybody give that?
Wait, how did you get the angle? Oh, wait,
You got it? I just need the magnitude. Is that right? 0.4?
Like, what are we, I missed a couple steps. Like, what are we drawing lines through and what are we looking for?
Right from the center, right here, to the
Okay.
point where you came in and normalized.
Yeah.
And measure this distance.
Oh,
And then go down to the bottom. I put up a bunch of videos that will be helpful. I'm going to give you a whole bunch of problems today. All right, we'll pick it up on Friday. I think I'm out of
yeah, I
time.
got about
Thank you again for being here.